Hello everyone and welcome to the video of my mini project here at Plymouth. It's kind of cool, so I think you'll like it. So I'll just get into it with a little bit of description of my code. If you want to skip that, you could skip over to the demo, which is towards the end. But just in case you want to learn how the code actually works, you can actually watch that part too. The project is basically a simulation of a drone. So it has one controller and a redundant controller, one which has an override over the other because there shouldn't be any clashing of controls. It's basically a fail-safe mechanism. So if both controllers do fail, the system actually shuts down and it doesn't cause any damage. So let's have a look at the code. Okay, so let's move on to the code. So the first thing I'm going to show you is the launch file. And the reason I need to write the launch file is because I'm using two Arduinos. And the problem with using multiple Arduinos is the node which automatically gets launched when I try to connect my Arduino to the ROS system is called a serial node. So its name is serial underscore node. And what happens is when I connect the second Arduino, the first one has to disconnect because there's a clash of names. So what the launch file basically does is it changes the names as I tell it to Arduino 1 and Arduino 2 instead of using the serial underscore node. So what this does is there is no longer a clash of names and I can actually launch the two nodes simultaneously. The additional advantage a launch file provides me is I can also launch another node with these two nodes, and that's the Joy to Arduino twist node, which is the node which converts the joystick messages into twist messages for the buggy. So let's have a quick look at the code that is running on the personal computer which you're using. So this code basically converts the joystick commands into twist messages for the Arduino. So I take in commands from data.axis0 and data.axis1, which are the x and y axis of the analog stick of the joystick which I'm using, which is the F710 wireless in this case. So this code actually scales the 0 to 1 commands which the axis sends me into 0 to 255. And why I've chosen to do this will be seen when we reference the other code which is actually running on the Arduino. As you can see here, I'm using a queue size of 10 in the publisher, and that's to make sure that the commands lost are as few as possible. I don't recommend increasing this size. You can actually even decrease it because whenever you flick the stick, you're actually going from an initial position to a final position, and you don't really need the values in between. So the queue size of 10 is basically upper limit. You can reduce it if you want. So right now we're in the ultrasonic controller code, which is burnt onto the lab model buggy. This code basically has to do just one task. It takes the distances that my hands are from both of the ultrasonic sensors, which are mounted on the lab model, and it sends them across the ROS system to the actuated buggy. That's a field model. So basically, this code converts the time which it takes for my trigger pulse to go and come back and result in the echo pulse. So it converts that into distance, and that distance is actually what is sent across the system. Also, you might notice that in this piece of code, I have pseudo movement functions, which I have also designed. So these were actually useful for debugging and seeing if the code is actually working right. And they actually serve another purpose. So basically what happens is if you don't power on the buggy using an external power source and just connect it using an USB, so in that case, whenever you run this piece of code with the movement functions not commented, what happens is whenever you are in the working distance, that is inside 28 centimeters as it's defined here, what will happen is the buggy would actually sense it and it'll try to move, but it doesn't have enough power. So what happens is you actually hear a buzzer ring, and that actually gives you a really good indication whether you're actually in the range or not. So I recommend keeping this code on and not powering your vehicle. And actually, this might be very useful in case you have to do any editing or debugging. Well, the biggest piece of code is yet to come, and this is it. This is the code which is on the field model, and I assure you, even though it looks kind of big, it's mostly movement functions, which is what make it big. And there are two movement functions, one for each sensor message that this buggy is going to receive. So the first set of messages is what comes from the ultrasonic controller. So most of the code is commented and it's self-explanatory, so I'll just briefly go over the logic. The ultra move command is the one which triggers when the ultrasonic controller sends a command. And what the ultrasonic controller is doing is it sends a -1 when I'm outside the 28 centimeter range, which basically means I'm out of range. If that happens, I go back and try to reach the joystick callback message, because if I don't, then it gets stuck in this loop forever because there is no change of value. The other set of movement commands is the ones from the joystick, and those are quite straightforward. They work basically using the X and Y values of the joystick, which are sent across using the ROS message in the form of a twist message. And again, what happens is whenever the commands are 00, which is the default for the joystick, that's when it's not in use, I try to reach the ultrasonic controller and see if it has sent a message. And this code is designed in such a way that the messages should not clash, because what happens is, in case I'm controlling the field model using, say, the ultrasonic controller, and the joystick suddenly sends a message, its callback is called, which causes an interruption. So that is not really useful, is it? Because it's breaking up the pattern which I'm sending it to. So the code is designed in such a way that only if one controller, once in use, becomes defunct, or it reaches a state where it's out of use, kind of, then it switches back to the other kind of controller and it tries to reach it and see if it has any kind of message, which is non-zero. Okay, so the last piece of code we are looking at is the ROS bridge code. This is basically an HTML document with two subscribers in it, which subscribe to the two topics that the controllers publish to. So this is for the joystick and this is for the ultrasonic controller. This is what you will see in your web browser window when you open the code. I'll just show you that. So it's opened in my Firefox. To view the data, you'll have to go into Tools, Web Developer, and select Web Console. So at the moment you can see that my console shows errors because I'm not connected. But if I'm connected, it'll show something like this when I'm actually publishing to the topic that is assigned. So this is when I flick the joystick, the joy commander publishes these kind of commands, and the ultrasonic controller publishes motor commands with values from 0 to 255 basically. Okay guys, so we are on to the demo. As you can see, we've already got the system running on the computer. This is my node graph. I've just popped this up so that you could see what's actually running. The thing is that the entire documentation is there in the README on my GitHub repository. So I just decided to skip the part which tells you how to run the entire set of nodes. So now we'll move on to the actual demonstration. So as you can see, this is my lab model, which is connected to the computer via this USB, and the other one which is sitting
on that little box there, that's the field model. I've actually put it on the box so that it doesn't run away. So let's get started. Now what I'm doing is I'm going to just move my finger over here in front of the ultrasonic controller. So as you can see, as I do that, one motor spins. And the thing what I have done is I've purposely used the left controller to control the right motor, because when my right motor spins, my vehicle actually turns left, so it becomes more intuitive. Now you can see the same thing with the other sensor. And now with both of them together, so both the motors are moving now. So this is basically how the ultrasonic controller moves, and as I move closer and further, the speed actually changes. And now I'm in the stop band, so it stops. So this is kind of like my stop band, about in this range. If I go closer, it moves forward. If I go further, it starts to move reverse. Now the other part of the demonstration is actually using the joystick to control this buggy. So right now I've got my wireless joystick. I've turned the mode on so that I can control it using the D-pad instead of the analog sticks. So this is kind of a lot more intuitive. So now I'm going in reverse. This is turning right and left. I'm not sure whether you can see the wheel spinning. Right and left, forward and reverse. Also, what the entire piece of code is designed to do is there's supposed to be an override. So when I'm actually using the ultrasonic controller, so I'm just putting my joystick in front of the ultrasonic controller because I only have two hands, I can't film it and activate it. So now I'm using ultrasonic controller, but when I use the joystick with the ultrasonic controller to move in directions other than what the ultrasonic controller is moving, it doesn't respond because the ultrasonic controller has an override over the joystick.
Well, I hope you like the project idea that I've come up with, as well as its implementation. If you did like it a lot, remember to hit the like button, which is somewhere down there, and make sure that you share it too, because it might be useful for other people. Just in case you do find it useful, I have put a link for all the code, which is in my repository in the description, so you can access it anytime you want. I hope you like the video. Thanks.